Okay, so we're talking about the fundamental theorem of calculus. And this is it. If f is an antiderivative of f, then this integral over here equals this difference of function values of f. And then this was actually what we focused on, integral from a to b. The difference is this first one is in function form. The final limit, or where we're going to end the value of x here, is variable. Okay, so it's x. Okay, so but the meaning is pretty much holds the same. It's just function form versus just amount form. So just one thing about notation. There's a compact way of writing this difference, and that is you just write function f, and then a vertical bar to the right, x equals b, x equals a. That means evaluate f at b, evaluate f at a, and subtract exactly what's in the red box. Okay? So that's just a shorthand notation. Oftentimes, you'll be solving the integral, and you'll write this first. You'll write your antiderivative, and then write now the limits over here vertically to the right, which has this meaning, and then you go on to write that stuff. So that's just notation. But what the most important thing though is the meaning of all this stuff. We worked for 2 days on building from the ground up, dissecting the meanings of all this. So we want to review that, and hopefully the homework gave you lots of practice at that. So here's a little exercise for you. So for each expression, we'll explain the meaning of the expression, include all specifics. So start with that first one there. So just literally, it's the integral from 1 to 2 of x to the 4th dx. But that is packed with meaning, and that's what we're talking about now. So what does that represent? What is the meaning of that? So you're going to verbalize that, write it out in a sentence. And then we're going to write a computable expression that gives its value exactly. And so we said this is the advantage of the fundamental theorem, is that a more abstract notation like that now can be written in a computable form. That was the whole point. And then solve or simplify as appropriate. So let's just work on the first one here. A, B, and C. Consult with the person next to you, especially on A. Take time verbalizing what that means. We'll do 1 and 2. First 2 there. Okay? Take about a minute or 2. Just the first 2. Go. Okay, let's, any volunteers let's go to the second one. So that's the integral from 0 to 8, 3e to the x dx. What is the meaning of that in the sentence? What is the meaning of that in the sentence, including all the details? Yes, ma'am? What's that? The whole thing is the rate of change. Okay, so one of the details is the 3e to the x is a rate of change function. Yep. So she's pointing out that 3e to the x is a rate of change function. Okay? That's part of it. What about the whole, just in a couple of words, first of all, the whole thing. Yes, ma'am? What's that? Okay, the sum of small changes that makes up what? That makes what? So if we sum up a bunch of small changes, we get what? Yeah, we didn't really use accumulation this semester, but if we sum up a bunch of small changes, we get a big change, right? A big change, right? So we get some amount of change. Yeah, and it's by summing up a bunch of small changes, okay? So we call that the net change of some quantity, all right? So that, first of all, it's the net change of some quantity. And we have a detail that that quantity is changing at a rate of 3e to the x. And then there's one more thing, yeah. Yeah, so it's the net change of that quantity as x changes from 0 to 8. So it's the net change. So here's one way to say it. There's different ways to phrase it, but this is the value of the net change of some quantity when x changes from 0 to 8, and the quantity's rate of change is 3e to the x. So you could jumble that around and say that in different ways, but it's the net change of some quantity, which is the sum of many small changes, like you said. As x changes from 0 to 8, the quantity's rate of change is 3e to the x. Okay, so can someone tell me the whole thing for the first one? Somebody new. Integral from 1 to 2 x to the 4th dx. What's the entire meaning of that? What's the entire meaning of that? Yes, sir.
The entire function is the accumulation
okay.
of between the points, and then the integral of 1 to 2 shows like between the x values of 1 and 2.
Okay.
Then the x to the 4th is the rate at which every y changes for every x change.
Okay.
And then dx is just the change in x.
Okay. So you got all the pieces, but then the whole thing together is what? Right, so it's a net accumulation or a net change of this quantity whose rate is x to the 4th as x changes from 1 to 2. So what is that? Is that a function? Is that an expression? Is it a value? What is that in terms of those choices? Yeah, it's a value. It has a specific value. And now we want to get that value. We want to know, what is that number? What is that value of the net change from 1 to 2 when the rate of change is x to the 4th? And what allows us to get that number? So this is more of an abstract symbolism or expression of that, expressing the sum of lots of little changes, right? The sum of lots of little changes. But we don't actually get this total amount, this total net change. How do we do it? Yeah.
We have to take the antiderivative of the rate of change function.
Okay.
And then plug 2 into that and subtract it from when we plug 1.
All right, right. So this is the fundamental. So the whole point, or not the whole point, but one very powerful point of the fundamental theorem is we take this kind of more abstract expression that is this some value, right? Some net change. It allows us to calculate it. Because that same net change can be expressed a different way, right? How can it also be expressed? As? So let's just go, let's call the antiderivative, for now, call the antiderivative capital F. So if the antiderivative is capital F, then this amount of net change is also expressed as f of 2 minus f of 1. So capital F is quantity function, and we know also to get the net change in the quantity, you could just take the final value of the quantity minus the initial value of the quantity, right? That, by definition of subtraction, that gives you the change from here to here, right? The change from one value to another is just the difference between them. So the question is, what is the antiderivative? If we know the antiderivative of x to the fourth. That's the quantity function for which x to the fourth is the rate of change, and that should be not so bad. So we're asking what function's derivative is x to the fourth? And you had some practice of that. Somebody knew? X to the fifth over 5. So that capital F function is x to the fifth over 5. Actually, x to the fifth over 5. So, yeah, plus any constant, right? So there's actually many, many possible answers. Because any constant along with that will still have that same rate of change function, x to the fourth. There's an infinite number of functions whose rate of change function is x to the fourth, all vertical shifts of the same quantity function, right? So now we're going to take f of 2 and f of 1, and we can even do it in this general form if we want. We don't have to. We can just assume c is 0, but even if we want, we can do 2 to the fifth over 5 plus c minus 1 to the fifth over 5. And what happens? It doesn't matter what some initial amount is when you're doing a net change. Your initial amount doesn't matter with a net change, right? Because those go away. Those go away. And we're just left with, what, 32 fifths minus 1 fifth? Is that 31 fifths? So that net amount of change that's being represented is 31 fifths. 31 fifths. If your rate of change is x to the fourth and you change from 1 to 2, you get a net amount of change of 31 fifths. Probably. I don't think so, though. 2 to the fifth is 32 over 5 minus 1 to the fifth. 1 fifth, 32. I think it's right. Okay. But actually, so I appreciate that because I will make mistakes. If you think there's a mistake, don't hesitate to raise your hand so we don't all dig a hole for ourselves and figure that out 15 minutes later, okay? If you think I made a mistake, please tell me. So I appreciate that. Thank you. All right. Questions on that? All right. So what about same thing with the next one? This is what? Some value. We talked about what value it is. It is a value. We want to find that value of a net amount of change. And so again, it's going to be what? It's just going to be the final value of the quantity function minus the initial value of the quantity function. Is another way to express that net amount of change. Instead of expressing it as the sum of a zillion little changes, right? That's what that expresses. The sum of a zillion little changes. It's just the final value minus the initial, so we'll call this one g. So this will be g of 8 minus g of 0. And the question is, what is g? G is any antiderivative of 3e to the x, or any function whose derivative is 3e to the x. Well, that's easy. So we're thinking, what function, if I took the derivative of it, would I get 3e to the x? 3e to the x. Right? This is that very, very special function where the value of the quantity is the same as the value of the rate of change. And then constants, we know, always just come along for the ride. Right? Constants multiplied, always stay around for the ride. So this would be 3e to the 8 minus, let's use that. So we could use that other notation. We could say 3e to the x evaluated from 0 to 8. Just to practice using that, so we recognize it. That means 3e to the 8th minus 3e to the 0. And when you plug 0 into something, you always get 0, right? Careful, okay? So this is, especially solving integrals, lots of times students just assume there's a 0. That means that whole term just drops out. It's just 0. Here's a perfect example. That's not true, right? That's not 0. So we get 3e to the 8th minus 3. So e to the 0 is 1. Another example, cosine of 0. That's not 0, right? Cosine of 0 is not 0. There's plenty of other examples. Just because you have a 0 as one of your limits of integration doesn't mean that that term is 0. Plug it in, make sure. Okay? So this one, same thing. We're going to use we need an antiderivative of sine x. So we're asking what function gives us a derivative of sine x. The next couple weeks is going to be all about antiderivatives. We don't want to learn a whole bunch of new rules for antiderivatives. We want to use all that we've learned about derivatives to do that. And we're just thinking in reverse. What function has the derivative sine of x? What function has the derivative sine of x? Negative cosine, right? And so negative cosine of 3/4 would be plus cosine of a half. So that's some number. And I want you to tell the person next to you the meaning of that number. What meaning does that have? If it was that integral originally. Take turns telling each other. Go. Does that help?
Yes.
Is that good right there?
Yeah, that's fine.
Okay. Somebody knew. That number represents what value? Somebody knew. How about in the back? Someone in the back 3 rows. Don't be shy. I'll just call on a shirt. All right, I'll call on a shirt. Let's see. Yeah. Right, okay, good. So she corrects. The only little mistake she said at first was that it's the change in x. Right, it's a change in some quantity. You could call it y, right? So it's the change in some quantity, the net change in a quantity, as x changes from negative a half to 3/4, if the rate of change was sine x. That's what that would be. Okay, so looking at the next one. So we know we want the antiderivative evaluated at 35, evaluated at 10. And so we look at this and we say, what function has that as its derivative? And that's harder. But you need to recognize what you're looking at. So you think about the harder derivatives that we did and the kind of results we got from harder derivatives. Can you recognize that as the result of some harder derivative, like some rule that we had? Okay, so you should see that that looks a whole lot like the result of a chain rule derivative. The result of a chain rule derivative. And so that's what we're going to spend some time on next. So that this is harder. So working backwards on these easy, x to the 4, 3 to the x, sine x is just a simple rule, and you just have to know it backwards. But chain rule is more complicated. Okay? So that's what we're going to spend some time working on, because many of our examples will be this. And so what we want to call this is, we call this undoing the chain rule. Right? So if this was the result of a chain rule derivative, then we want to learn how to undo the chain rule and get that original function whose derivative was that. Okay. So we're gonna before we'll come back to that example or one very similar to it. So before we do that, let's just do some more practice of chain rule. So let's just practice so we really have the chain rule down, because if you really have a strong mindset about chain rule, that's going to really help you with this undoing the chain rule. So for the first one, don't do quotient rule, right? We want to make this a chain rule problem. And what is chain rule about? It's about composite functions. Functions plugged into other functions. Functions plugged into other functions. So don't do quotient rule on this first one. So maybe start by rewriting it so that it's a composite function, right? Composite function is like f of, or g of f of x. So if you're not sure, then maybe get some assistance. You don't want to start working on the derivative until you have it in the right form to do the chain rule. Okay? So work on these for a couple minutes to refresh your memory on the chain rule.
Natural log.
Okay, so these are all ready to do the chain rule. Remember, the chain rule is you're going to do the rate of change of the big picture function, right? The exterior function, rate of change, leaving the interior as it is, and then times the rate of change of the interior. So this first one, so say dy dx equals rate of change of something to the negative 1/2. Negative 1/2 to that, or of that thing, to the negative 3 halves. Are we done? Times minus negative 2 pi. You're so smart. Okay. All right, so observation. One term, one factor. The derivative is how many factors? Factors are things multiplied together. Okay? How many? So we got just one thing there, and now how many things do we have? Really? 2, right? So this is just all one, what we call term or factor, but now this has 2 factors. It has this thing to the negative 3 halves and 5x to the 4th minus 1 over x. So going backwards, we're on the lookout for what? We're on the lookout for something with 2 factors, and it's, when we do the antiderivative, it's going to become 1, right? It's going to become 1. All right, next one. So here y prime equals, so exterior function, rate of change is? Stays the same. And then times rate of change of the interior, 15/4 I heard, x to the 1/4. So if we're doing antiderivative, look, we're on the lookout for 2 factors multiplied. Antiderivative will be 1 factor. Last one. Exterior, rate of change of the exterior function is? Oh, ye masters of derivatives, right? Okay, so having a really strong understanding and ability to do the chain rule is going to be the key to having to be able to do the undoing the chain rule. Seeing these and recognizing what you had before. But I'll give you, so we're going to give you a little bit of structure in this. You don't have to just look at these and be able to come up with it right away. If you can, that's great. That's great. You can just sail right through this. But I'm going to give you a little structure on how to reverse this, how to move backwards. So the chain rule says that if you have g of f of x, that the derivative is the rate of change of the exterior, keeping the interior as it is, times the rate of change of the interior. We just did 3 examples of that, right? Therefore, the antiderivative is going to be something like this. You're going to have that product of functions, and you're going to collapse it back into the one term, right? So here's the key question. What will you focus on in the rate of change function to recover the amount function? Okay? Will you focus on, so look at the amount function. This is what we want, g of f of x. So what are we going to focus on over here to recover g of f of x? What has the information we need? Is it exhibit A or exhibit B? Which exhibit has the information that we'll need to get g of f of x? Exhibit A or exhibit B? You should be thinking A. It's so close to it, right? It's almost the same thing. It's just one, there's only one difference. Exhibit B does not have the information that you need. Why? Because there's nothing about function g. There's nothing about function g in exhibit B. So, we are going to focus on this because it's so close to our answer, right? Those 2 terms are going to collapse back into each other, and it's going to be really close to that g prime f of x part. All right, so what do we need to do? If once we find that g prime f of x, there's only one thing to do, which is what? Find the antiderivative of g and leave f as it is, and we're almost done. You see that? So we're going to write the antiderivative of the exterior function, keeping the interior function f as it is. And then we might have a little mess to clean up, but that's the easy part. Okay, so just as an example, that E one that we just did, well, we had tell me what that was, the second example. Okay? And that was e to the 3 x to the 5 over 4 times 15 fourths x to the 1/4. So just thinking about this process, here we've got this rate function, rate of change function. We want the antiderivative. We identify that the g prime f was this, and then what do? We do the antiderivative of g, or the antiderivative of e to the something, right? The antiderivative of e to the something is e to the something, and there it is. Make sense? So we're just thinking backwards. We're thinking backwards. I'm giving you some structure, but if you can bypass the structure and just solve these, that's what I'm encouraging. So the structure is just to get us started, but then if you can just start to see them and you're just looking for that key factor and doing the antiderivative and then cleaning up the mess, that's what we want. Okay? So here we go. First example. X cubed times 8 plus x to the 4th to the 5th dx. So we want to think like this. This is like g prime f of x times f prime of x, the result of a chain rule derivative, and I need to recover the original g of f of x. So what do I want to find? I want to isolate, or I want to focus in on the part of this antiderivative here, the part of this rate function that is g prime f of x, where the other part is f prime of x. So am I going to focus on exhibit A or exhibit B? You should see exhibit B. And as a check of that, then the other part, this x cubed, should be the derivative of, or something, essentially the derivative of the inside here, right? Is it? Is x cubed essentially the derivative of 8 plus x to the 4th? Yes, we're off by a factor, and that's no problem, right? That's no problem. So yeah, x cubed is essentially the derivative of 8 plus x to the 4th. Therefore, the x cubed is the f prime part. All right, so what's our attempt going to be? Our attempt is going, well, like we said, now that we've got our right focus point, we're just going to do the antiderivative of the exterior function, and we're almost done. What's the antiderivative of 8 plus x to the 4th to the 5th? What's the antiderivative of the exterior part of that? The exterior part of that. So what is the exterior? It's something to the 5th, right? So the antiderivative of something to the 5th is what? 1/6 times that something to the, here's our first attempt. Our first attempt at this, 1/6, 8 plus x to the 4th to the 6th. Notice, remember, two things multiplied together collapse back into one. So what are we going to, so we know that's at least on the right track or close. How can we check it? We're going to take the derivative of it, right? If we take the derivative of it and we get exactly what we started with, we're done. Our attempt was right. So the derivative is, so we're going to take the derivative now. Take the derivative, we get 6 times 1/6, that's just 1. We get 8 plus x to the 4th to the 5th. And here's where we got to know our chain rule, right? So this is chain rule now, times 4x cubed, and we compare. Is it exactly the same as what we started with? All right, we've got this extra 4. So we're going to go back and adjust our attempt so that if we took the derivative, the 4 wouldn't be there. How are we going to adjust the initial attempt? So if we took the derivative of it, the 4 wouldn't be there, and we have it. We're going to need another 1/4, right? We're going to divide that initial attempt by 1/4. So attempt number 2, 1/4 of what we had before. And then we could simplify that as 1/24. And if we're shaky or not confident, we want to check again, we take the derivative again. Take the derivative again. Again, you got to know your chain rule well. And you're going to get exactly that. So now, this is there's no limits of integration. So what does it mean? It means every antiderivative, or every possible quantity function whose rate of change is that. So we need plus c. And if we had limits of integration, and this was a value of net change, we could find that value of net change now by plugging in doing final minus initial, right? Final value of the quantity minus initial. Questions on this? Yes, ma'am? Because in our initial attempt, when we took the derivative, we got this extra 4 right here. See that? We don't want that because there was no 4 in the. So I'm gonna change my attempt. This is attempt number 2, such that when I take the derivative of it, the 4 won't be there. So I need 1/4. So in that, again, if you're not sure, take the derivative. You can just keep taking the derivative of your attempts until, and use that information to adjust. Okay, so some of you learned something called U substitution. This is an alternative to U substitution. I like this a whole lot better, and I'll explain why. First of all, U substitution is like, it's like learning something new instead of just making an adjustment to something you already knew. So this is all based on your knowledge of something you already knew, the chain rule. So U substitution is kind of like learning a whole new technique. The more important reason I like this better is when you get good at this, you can do it in 1/4 or 1/3 of the time that all the U substitution takes. Okay? I really, really encourage you to learn this. Because when you get good at it, you just see that as a result of a chain rule. Many of you will just be able to go right to this answer. You'll see, oh, there's going to be an extra 4 in there. So I'm going to do 8 plus x to the 4th to the 6th. I'm going to need the 1/6, and I'm going to need the 1/4 also. And then you can just write it down. And that will be so much faster than all the work it takes to do U substitution. Okay? And again, it's based on your knowledge of, it harnesses your knowledge of the chain rule instead of learning something all new. We'll do U substitution later for some other types. But if it's the result of a chain rule derivative, I really encourage you to learn how to undo the chain rule for efficiency's sake. Okay? More examples. Here we go. So, what's different about this one? Yeah, so with chain rule, we know we're used to getting a product. Well, we have a quotient. How are we going to handle that? Yeah, make it a product, right? All quotients can be made into a product, exactly. So we can make a product. So we're going to say cosine x, and not even 1/. What can we say? Times. What exponent is that if it's to the power 4 in the denominator? -4. So we can do sine x to the -4. Now it should look like the result of a chain rule. It should look like the result of a chain rule. Okay, so let's see if you can do it. So this is actually kind of easy. Kind of easy. Everyone do it. Remember what you're doing. You're focusing in on what the g prime of f is, and then you're going to do the antiderivative of g prime. Okay, Hurley shirt. Did you get it? No, Hurley shirt, you. Yeah. What was your first attempt? Integral of cosine? Now what are we going to focus on here if we're going to undo the chain rule? Okay, so what's your first attempt going to be? But we're going to do antiderivative, right? So it won't be negative 1/4, but negative 1/3, right? So it'll be sine x to the negative 3, and we're going to need a negative 1/3. That's our first attempt. So this check is kind of like the whole, doing the check is the whole point of this, that we just thought backwards of this process. We're thinking, is this function, is its derivative this? So we'll take the derivative. So when you take the derivative of this, do you get exactly this? We done? Nope. Times? Is that exactly this? Thank you. So is this now exactly what we started with? Yes. First attempt worked. We're done. Okay. Again, the goal is you're not following this procedure, but you're seeing it as you're undoing the chain rule, and you're just writing down the answer, and then cleaning up the mess. That's the goal, that many of you will just be able to write these down. Instead of step 1, attempt 1. Step 2, take the derivative. Step 3, attempt 2, right? So that's only just to get you thinking about what we're really doing, which is just recognizing that as the result of chain rule. What function will have that as its derivative? One more, go. So this one is, what has as its derivative something to the negative 1? What has as its derivative something to the negative 1? So you got to remember. So this is the one case of a power where it's different. And if you try to do the power rule, what do you get? 2 minus 9x to the 0, and then 1 over 0. So there's all kind of warning bells here. What's something to the 0? So this, actually your x goes away because that's 1, and then you have 1 over 0. Okay? Only my daughter can divide by 0. None of you can. She's brilliant. She can do it. You can't do it. So, warning, warning. Something's different here. What has as its rate of change or derivative something to the negative 1? Yes, sir. What's that? Yeah, ln, right. So it's going to be ln of what? Our attempt is ln of that thing. ln has as its derivative to the negative 1. And now, when we work backwards, we're going to need absolute values. Don't have time to explain that. But whenever you take the natural log as an antiderivative, you need absolute value. That's a good discussion for another time. Okay, and then we need to check that and clean up the mess. So we know we have this 6 here. What else are we going to have when we take the derivative? We're going to have times -9. So how do we compensate for that? Divide by -9. So that's the goal, to be able to do it that fast. Natural log of that thing, we have the 6, and we know we're going to need a -9 also. So you can simplify -2/3, natural log, absolute value, 2 minus 9x plus c. Okay, starting now, we're going to have web work, online homework. Blackboard will have all the details, okay? So just go to the homework on Blackboard, we'll have all the details.